was a greedy algorithm for finding minimum spanning trees. There's a second algorithm, which, as we described last class, works better for sparse graphs, called Koskals Algorithm. And Koskals Algorithm, what does it do? I think I went through the animation last class, the example. But what would Koskals Algorithm do? We sort the edges from smallest weight to biggest weight. We insert the edges into it, smallest weight. 2 is the smallest weight. 2 is the smallest weight. 3 is the smallest weight. 4 is the smallest remaining weight. Dot, dot, dot. But oops, that creates a cycle. That can't be part of a spanning tree, right? There's another edge of weight 4. That's good. That gives me another vertex. An edge of weight 5. Oops, that creates a cycle. 6. Oh, here's another edge of weight 5. That was good. Something of weight 6. Can't find it. 7. Well, I could add this thing, but it creates a cycle. I could add this one, and it doesn't, and now every vertex is reached. Here is a minimum spanning tree of the graph. Any questions about how Koskals algorithm works? Okay? Any questions about that? Questions? What can I add now to not create a cycle? Ah, what you're saying is I didn't have to add this 7. You're saying maybe you really want, I could have added this 7 first. That would create a different spanning tree, a different minimum spanning tree. But they're both of minimum weight. Does everybody agree with that? We have no reason to think one of them is better than the other. You like one of them better than the other? Seem to be, they're alternate minimum spanning trees of the graph. Any questions here? Okay. Questions? Well, Koskals algorithm, so Prim's algorithm is growing a minimum spanning tree. Starting from one point, Prim's algorithm was growing out from that point. And as it worked through it, it was always leaving us with a partially constructed spanning tree. Prim's algorithm is selecting edges in terms of desirability. And as it goes along, we've got a forest of little trees, not necessarily connected. Does everybody see that? These lightweight edges could be popping up anywhere else in the graph. Okay? Any questions about that? Okay? Any questions? Okay. So what does Prim's algorithm look like in, just keep going through this a little bit more. The first question is, why is Prim's algorithm correct? Why doesn't it make any mistakes? Okay? How many people believe the idea of the algorithm, understand the algorithm well enough to say, yeah, it's probably correct? Okay? It seems reasonable. Who here doesn't understand it to the point they don't see why this is constructing a spanning tree or anything like that? Okay? So you believe it. What would be the proof that it is correct? That you never go wrong. Basically, the heart of Prim's algorithm, Koskals algorithm, is you're adding edges from cheapest to most expensive. And for correctness to work, it means that you never went wrong. That as you go through these things and insert them one by one from cheapest to most expensive, that in all cases, the partial tree you have, the partial forest, if you wish, that you have so far, is contained within some minimum spanning tree, right? You're picking these edges, these components for your minimum spanning tree. The algorithm is correct so long as you keep picking them. You've never gone wrong. You've never added another edge to the point where the set of components that you have already picked are wrong. Okay, there is no minimum spanning tree that contains it. Any questions here? So what is the proof of correctness? It's something quite analogous to the idea of the previous proof of correctness. So if you didn't like the previous proof of correctness for prims, we're going to use the same kind of an idea for Koskals. So let's look one more time. The idea is proof by contradiction. What does proof by contradiction mean? Assume it is wrong. Koskals algorithm is wrong. Okay? If Koskals algorithm is wrong, then what do we know? There is some graph where when you run Koskals algorithm, at some point it makes a fatal mistake. It has added a collection of edges, okay, such that, here it is, Koskals algorithm is adding edges, and at some point you can go, I added this edge to what I already had, okay, and before I had it, the edges I picked were in fact in some minimum spanning tree. But now when you add this, these edges together cannot be in a minimum spanning tree. Okay? There is no way to extend this thing to make it a minimum spanning tree. Okay? Any questions about that? So how would our proof of contradiction go? It's actually the same idea of what we had last time. What did we do last time? We said, okay, this isn't the minimum spanning tree, so give me the minimum spanning tree. And it's going to, what's the minimum spanning tree? Well, it's going to include all the other edges I had picked. And it's going to include some other stuff, okay, right, to finish making it a spanning tree. Now it's a spanning tree. Everybody agree? What happens if I add that poison edge to what you tell me is the cheapest spanning tree? What happens? It creates a cycle. Does everybody agree with that? You take any tree, you add an edge to it, it creates a cycle. Does everybody agree with that? So what is interesting now about that cycle? Can I take that cycle and do something to it to make the spanning tree lower? Okay? I wanted this edge. Okay? Was at least one of these other edges, either these edges on the cycle that were there that you added, was at least one of those edges added after I added the poison edge? Okay, remember there was a set of edges that you said I did okay on. Then there was the, you messed up. And then here, dummy, is the rest of the spanning tree, right? How do we know that at least one of the edges on this cycle that I have in green had to have been had to have come not from my partial tree that I gave you, but from the rest of the stuff that you filled in? Okay? Is it possible that all those green edges were in the spanning tree, in the spanning forest I was building from Prim's algorithm? When I decided to use Prim's algorithm to insert the red edge, is it possible they were all there? Okay, you say no, why not? It would have created a cycle, right? And I would never have inserted that edge if it created a cycle, right? So it's pretty clear that at least one of these edges, okay, has to have been something I haven't yet considered using Koskals algorithm. Does everybody agree with that? I'm inserting edges, cheapest, next cheapest, oh, create a cycle, forget it. Next cheapest, create a cycle, throw it out, right? And then I got to the red edge and I got a ding. Right? I wanted to put that thing in there, meaning that so far, this vertex and this vertex were in different components that I was building. Does everybody agree with that? I would never have put that thing in the graph if they were in the same component. So what does that mean? Somehow, to complete the spanning tree you tell me is correct, I had to have some other edge here that I didn't consider. Does everybody agree with that? And what is the property of that edge that I didn't consider? What do we know about, yes? The red edge is the one that I wanted to put in here. This is the one that they're put in, that they put in instead of me. But could this edge possibly be lighter than my edge? No, because I sorted them from cheapest to highest, right? The reason I looked at the red edge is I know that the red edge had to be less than the blue edge, right? Does everybody agree with that? So what happens if I add the red edge and delete the blue edge? Now maybe you can't read the drawing. But everybody see what would happen? What will happen to the cost of the spanning tree? What? It has to go down, right? I had a tree, it cost a certain amount. I rip out an expensive part and I replace it in an unexpected part. It's still connected. It's of lower weight, right? Now, how could I give you a lower weight of something that is the minimum spanning tree? You told me that your algorithm, that the minimum spanning tree, and I didn't find it. Well, look, I have found something cheaper than your minimum spanning tree. So you had to be lying to me. So the assumption that Koskals' algorithm was wrong is wrong. If it's wrong that Koskals' algorithm is wrong, Koskals' algorithm is right. And that is the idea that we're doing here. Any questions about that? How many people see it? How many people don't see it and want to see it? Let's see it again. Okay, I hear one person. Okay, let's try it again. Let's read through what it says on the slide. No. Okay? We're going to do proof by contradiction. Suppose Koskals' algorithm is wrong, then there's a graph where it fails. And if so, there is a first edge where it fails, right? Meaning that when we add this edge xy to the set of edges we already took it in that you said were okay, that now we get something that can't give us a minimum spanning tree. Now at the moment we added edge xy, here was x, here was y. There could not have been a path in our spanning tree going from x to y. Because if there had been, Koskals would have tried to add it and said, whoa, they're not in separate components. They make a cycle. You don't add it even though it's cheap. Okay? So we know that we wanted to add it, meaning there had to be some gap, okay, in a path, other path from x to y, right? Now, if we then add to the optimal tree our new edge, our proven edge xy, the one that you dinged us on, it will create a cycle with your tree, because adding any edge would create a cycle with your tree. And if I delete any edge from the cycle, the graph stays connected. Does everybody see that? This is sort of an important point. Once I have a cycle, I can delete any one of those edges, and it stays in one piece. Does everybody agree with it? It stays connected. Does everybody agree with that? I can delete this edge. Look, it's connected, right? So what is the whole point? If I add it back, it will have created a cycle. At least one edge will have been added to the cycle after me, which is one of these blue edges. There might have been many of them. There's even one over here, okay? But all of these guys had the property they were added after the green edge. And therefore, they had to be heavier. So the claim is that I can now delete the heaviest of these guys, or any of these guys, in fact. Replace it with this, and I've got a lower cost spanning tree. And therefore, you were lying to me when you told me you had the minimum cost spanning tree. Deleting the heavy edge from that augmented tree, the tree plus my edge, gives me a better minimum spanning tree, and this is a contradiction. Any questions about that? Okay? This is why minimum spanning tree is correct. Okay? Any questions? Koskals' algorithm is correct. Any questions? Okay, good. So how much time does Koskals algorithm take? Let's think about the running time of Koskals algorithm. What was Koskals algorithm? First thing was sort the m edges in the graph by from cheapest to highest. Does everybody agree with that? If there's m edges and we have to sort them, how much time does it take? How much time does it take to sort m of anything? M log m. Does everybody agree with that? You give me n edges to sort. These edges have weights. I'm sorting the weights, right? It's no different than anything else. This is how much time it takes to sort. Now then, I've got an algorithm, something that's going to be doing what? It's going to go around for potentially every edge in the graph, considering them from cheapest to most expensive, okay? Inserting the edge into the graph. What is it that I have to test when I insert the new edge into the graph? Okay? Did I insert it between two vertices of the connected component? Is everybody right? That would be one way to do it, right? So how could I tell if I create a cycle? Let's think about it. How could I tell if inserting another edge into my graph so far creates a cycle? How do I test if a graph has a cycle? DFS, BFS, right? I could take the current tree that I've built, or subgraph that I've built, and do a depth first search to see if it has any cycles. Before I inserted any edge of my tree in there, it has no cycles, right? I now insert an edge in here and saying, hey, does it make any cycles? I do it reversal. If it made it a cycle, I would take that edge out of my tree, right? So in general, I've got a vertex here that I'm doing is I'm going to be taking my current graph, which has less than n edges. I'm now going to insert another edge into it and ask if this graph has a cycle. How much time does it take to do a traversal on a graph on n vertices and m edges? N plus m. And what if I only have n edges? How much time will that take? Well, what's n plus n? If m is n. N plus n is n. Everybody agree with that? So we'll linear time, order n time, to test whether or not inserting this thing into the tree that I've been building makes a cycle. Does everybody agree with that? This is what I want people to see how I am doing it. So if you're saying, I don't see how to do it, this is what I want to see you see how I'm doing it. How can I test that I'm creating a cycle? I showed you before how to test if a graph has a cycle. And it took time linear in the size of the graph. The graph that I am building is only a tree. It has at most n edges. And so I claim it'll take order n time to test for each edge whether adding it to the tree will create a cycle. If it didn't, all the more power to it. I'm going to keep it there. If it did, I'm going to take back what I just did. Okay, and start with the next edge. For each of the m edges, I am spending order n time. That gives me an order n times m algorithm. Any questions about that? How many people here see why, as implemented now, Koskals algorithm is n times m? Why isn't it n times m plus m log m? That's a good question. Because the first one is bigger. Do we believe that? Let's think about this for a second. Is the m's we agree cancel, right? That's not going to be part of the comparison. The real question is log, is n bigger than log m? Now we agree n is bigger than log n, right? Is m equal to n? M is the input number of edges. Are there only n edges in the graph? Can there be more than n edges in the graph that we're giving as input? Okay? If I want to find the minimum spanning tree of a graph, can that graph have more than n edges? Oh, maybe I've crossed that right. Give me an input graph. Can it have more than n edges? N is the number of vertices. Is there a graph on n vertices with more than n edges? No? Yes. Okay. How many edges can it have? What's the most number of edges a graph on n vertices can have? Okay, let's take a look at this again. Come back here. I give you a graph on n vertices. There's n people in this class, right? How many possible friendships can there be? A friendship is a pair of people, right? How many friendships can there be in this class? What? Every friend can be the friend of another one. Does everybody agree with that? So how many friendships can there be? Something that is theta of n squared. Does everybody agree with that? I claim the maximum number of edges in any simple graph, okay, on n vertices has to be n squared. How many people believe that? How many people don't believe that? How many people don't answer? Go back and do it again, okay? How many people here see why a graph on n vertices can have up to n squared edges? Raise your hands. How many people here do not see why you can't, a graph on n vertices can have up to n squared edges? How many people didn't raise their hands? Okay? So let's go through it again. Okay, does everybody see that a graph on n vertices, the edges are the pairs of those things. There can be n squared pairs on n vertices. So a dense graph can have n squared edges. How many edges will a sparse graph have? What's the sparsest graph you can build? Well, sparse means infrequent, right? Dense means that there's a lot of things going on, right? So dense means that there's as many edges as possible. Sparse means there's as few edges as possible. How few edges can there be in a graph on n vertices? 0, potentially, right? A friendship graph among a bunch of very undesirable people would have 0 edges, right? The smallest connected or interesting graph probably has n edges. So that's what we usually mean by a sparse graph. So graphs can have between 0 edges and n squared edges. And a lot of interesting graphs happen to have n edges. But in fact, m can be m is order of n squared. That's really the interesting thing, right? So now tell me something. Which is bigger, m log m or m times n? Which is bigger here? Let's think about this. The m's don't really matter here, right? Because those are sort of the same on both sides. Okay? Now, if there was no connection between n and m, this question would be unknowable. Which is more money? Okay? How much you own or the log of what Bill Gates owns? Okay? I don't know, okay? I don't know what your wealth is well enough, but it's not obvious to me. It's immediately obvious to me. Well, you know, something like that. Okay? Actually, I think you probably do have more than the log of Bill Gates' wealth. Feel good about it. Okay? But that's a separate question. Which is bigger, though, when we know that m has to be less than or equal to some constant times n squared? Let's think about this. What is the log of n squared? That's 2 log n. Does everybody agree with that? Now when we ask which is bigger, 2 log n or n, which is clearly bigger? N. Does everybody see that? So the point is that this is bigger than that. So this plus this does drive the complexity of this particular implementation. Any questions about that? Yes? Yeah? Well, what I'm saying here is that if I have a graph on 3 vertices, the number of edges is less than some constant times n squared, to be precise, for n big enough, greater than n naught. You want to say, is the number of edges in a graph on 3 vertices less than 9? How many edges can there be on 3 vertices? 3. 3 less than 9? Right to me. Okay? To be precise, the maximum number of edges you can have is n times n plus 1 divided by 2. That's n choose 2. Is that right? Let's look at that. If I have 2 vertices, what's the number of edges I can give? Actually, let's make it n minus 1. Okay, if I have 2 vertices, how many edges can there be between them? 1. 2 times 2 minus 1 is 2. Does everybody agree that that one looks right? What about 3? What's the maximum number of edges I can get here? That would be 3 times 2 divided by 2. That works out to be 3. Is that right? Let's do one more. What's the most edges you can have on 4 vertices? Chunk, a chunk, a chunk, a chunk, a chunk. Does everybody see that? What does that work out to be? 6. 4 times 3 is 12, divided by 2 is 6, right? So that says that the maximum number of edges is this, which is roughly n squared. Again, I like to think big O-ish. Why do I think big O-ish? This minus 1 thing is complicated. But every vertex connected to every other vertex, n times n, that I can deal with. Any questions? Okay? So we've lost a little bit what the vision here is. Okay? My claim is that with this implementation of Koskals algorithm, it will run in n times m algorithm time, because this is the bigger part. The interesting thing that actually I don't think I'm going to show you, but it's in my slides and it's in the book, and maybe if I had more time, maybe I'll go back to it. There is a clever way to make it so the running time is actually this. Okay? And it has to do with good data structures. Okay? The two things that we are really doing in Koskals algorithm, okay, is testing our 2 vertices for the edge that I'm interested in. Do they lie in the same connected component? If I had a fast data structure that would tell me, given my tree so far, here is the edge. Are both ends of these in the same component? If I could answer this question in log time, and if I could then add that edge to the graph in log time, okay, then how fast would Koskals algorithm be? The 2 things I have to do is to test whether or not the 2 vertices lie in the same component, and also to then take 2 vertices, 2 different components in the graph, and add an edge between them to make them one component. If I could show you how to do both of these operations in log n time, I claim Koskals algorithm would now take order m log n. Why is that? Because what was Koskals algorithm doing? Okay. Basically, it sorted the edges in something like m log n time. Then it looped through. Get the next edge. Do they lie in the same component? If that took log n time, add that thing to that edge to the tree, meaning merge the components. If that took log n time, this loop would go around m times. If we could do these operations fast with a clear data structure, it would take order m log n time to find the minimum spanning tree. And my claim is you can, and my claim is that the data structure is in the book and in my notes, but I can tell people's eyes are getting tired, and they don't want to hear about it. Who really wants to hear about it? You want to hear about it? Okay. Maybe you'll hear about it. I want to move on to the next one because it's more important for the homework at this point. Okay? But if I get time, okay, I might go back to what the data structure is for doing this. Okay? Any questions? It's a famous data structure, just so you know the name. It's called union find. Okay? And I think I'm going to resist the temptation to go through it. Okay? Because I want to get going to shortest path. Any questions here? Okay? Any questions about that? Okay, let's look at today's, at the next set of lecture notes then. What's that, escape? Let's go back here. Boom, boom, boom. Okay. So let's start a little bit fresh, because again, there's going to be some, you don't want to get caught in the technical details of some of these things. Understand big pictures. In shortest path, there is a big picture here that's going to be sort of important to understand. But first, let's do the problem of the day. I think now actually should be pretty easy. What was the problem of the day? The problem of the day said, suppose we are given a minimum spanning tree of a graph. So, ka-chunk, here is a set of vertices, and here is, in fact, the minimum spanning tree. And then we are given another edge. Okay? Someone now adds this edge to the graph. Another friendship gets added to the graph. And we now want to find the minimum spanning tree of the new graph. Okay? How can we find the minimum spanning tree of the new graph efficiently in linear time? Okay? What do we have to do to find, if you gave me the old minimum spanning tree, okay? How would you, and you give me another edge to insert, how can you tell whether or not, find the new minimum spanning tree quickly? Any ideas? Okay? I could take that edge, add it to the whole graph, and recompute the minimum spanning tree. But that would take something like order m times m, right? What could I do to reconstruct the minimum spanning tree if you add a new edge to it? Give me the old tree and you give me a new edge. What can I do to find the new minimum spanning tree? Minimum spanning tree of the new graph. Any questions? Yes. So let's think about this. You're telling me that suppose you want to take a look. This edge has weight 5. This edge has weight 10. This edge has weight 12. Okay? You're saying it has no bearing on the minimum spanning tree because you looked at its neighbors. Is that right? Does this mean that now that edge is not interesting, or might that edge be interesting to us? What? Well, where can it fall apart? Does everybody see that we, just looking at what we have now, we don't know whether or not edge 12, the 12-weight edge, is going to change the minimum spanning tree or not? Under what condition would we know that? What do we have to look at? the whole cycle. Does everybody see? If I now look at this one, and this thing is 17, is 17, and this one is 3. Did adding that edge change the minimum spanning tree? You bet you, right? I can add the 12 and I can drop the 17. Does everybody see that? It's a question of, so what is the condition? If I add that new edge, if it is at least as big, if it is not the biggest edge of all the others in the cycle, I'm better off adding it and replacing the heaviest edge in the cycle. Does everybody agree with that? What if there was another edge out here? This one had, let's say this one had a wedge of 7, and this had an edge of 100. Does inserting the new edge do us any good for the minimum spanning tree? No, we would like to replace it. But adding that edge doesn't enable us to remove the really, really heavy one. It only allows us to remove the heaviest one of the cycle. Does everybody see that? So this would be my algorithm or my idea of how I maintain the minimum spanning tree when I increase an edge, when I add another edge to the graph. Any questions? Yes? Okay, so what is our problem? Let's make sure people are getting the problem. Try this Skiena chunk. The problem is this. I am giving you a graph. And I'm giving you a minimum spanning tree on that graph. Here's the minimum spanning tree. I happen to know it. There were, of course, some other edges in the graph as well that weren't in the minimum spanning tree. Right? Now, I add another edge to the graph. And I tell you, find me the minimum spanning tree of the graph. How would I find what the new minimum spanning tree is? The claim is that this new edge will only help me if it lowers the heaviest weight edge, if it is not the heaviest weight edge on the cycle it created. Because if it was lighter than some other edge, if this edge was lighter than that edge, I would be better off adding this edge to my spanning tree and deleting this one, adding it back to the graph, but not the spanning tree. Any questions about that? Yes? Yes, yes, to get me a spanning tree back, if I'm going to take this edge in my spanning tree, it means I have to delete, it's going to create a cycle when I edit. I'm going to have to pull somebody else out. And the one I should pull out to make it as small as possible, the heaviest one. Everybody see that? Any questions about that? Questions? So I have to find the cycle in linear time. How would I find the cycle in this graph? Okay? Think about that. How would I find, if you were giving me a spanning tree, there are a couple of different answers here. Here you're giving me a spanning tree. And I am later going to add an edge from S to T. And I want to know what edges are on that, would be on that cycle with S to T if I added it. Someone give me an algorithm to do that? Yes. I could do an edge, I could add the edge to the tree, do a depth first search from here, and wait for a back edge, right? Is there any other way I could do it, actually, to find that cycle in a tree without adding the edge? How would I do it? Suppose I did a breadth first search without adding the edge from S. I know the edge is going to go from S to T when I add it, right? The cycle that's going to be created is what? That new edge and what? The path from S to T, is that right? Is there only one such path? If it's a tree, there's only one path between anything. Does everybody see that? That's an important property of trees. Between any vertices, there is only one path in the tree. Okay? So it's enough to find that path. How could I find the path from S to T in that tree? Any ideas? How would I do it? What? Depth first search? Or what about breadth first search? Same difference, right? The moment I discover this vertex was discovered by somebody, right? This vertex was discovered by somebody, discovered by somebody, discovered by somebody, ding, ding, ding. Any questions about that? Okay, yes. Well, okay. So the question, you're now asking a highly specialized question, does it pay to do this kind of thing? I don't know anybody who's paying someone to maintain a minimum spanning trees after people add extra edges. So this we'll call a theory kind of a problem, more than a big practical thing to do. Okay? But that's the reason why it works is because of the mechanics of why minimum spanning trees are important and good things. Okay? This gets to the same idea as to why the minimum spanning trees were correct, right? It has to do with the fact that on any cycle in the graph, we'd better delete the heaviest edge. Okay? That's really what both of those other algorithms are in some sense saying. Okay? Any questions about it? Is it possible I find two paths from S to T in a graph, general graph? The answer is yes. In a tree, the answer is no. Note that the minimum spanning tree is a tree, right? If I say, who's the best student in this class? I can guarantee you that the best student in this class is a person. Does everybody agree with that? Anybody doubt that? Surprise. Okay? The minimum spanning tree is a tree. One thing that is true of every tree, look at it, I'm going to draw a tree. By definition, see how I'm drawing the tree? There's branching, but there is no cycle. If there are two ways to get between a point, what does that mean? It means there is a cycle, right? Isn't that exactly what a cycle is? Certainly the graph may have multiple cycles. So let's think what our problem really is here, to be precise. Here is our graph G, which has lots of edges in it, right? And certainly has cycles. Here is the minimum spanning tree of G, which is going to be a tree, right? Everybody see that? That's a tree. Okay? Now I want to know what is the minimum spanning tree of the graph plus an edge, right? Now here's the question. Adding that one edge to the graph is not going to cause any change to the spanning tree, except with respect to the cycle that it had there. Okay? The argument here is that adding that edge to the spanning tree, the only change that it's going to the graph, the only change that graph will have that will have to the minimum spanning tree is in the cycle that it when you added it, right? If I add an extremely heavy edge to the graph, is it going to change the minimum spanning tree? If I add an extremely light minimum edge to the minimum spanning tree, is it going to have any propagation effects outside that cycle? And my claim is no. Okay? Why? Because, well, let's think think about why it is, actually. Why is it that the case? Think about Koskals' algorithm. Koskals' algorithm is a correct way to create minimum spanning trees. Does everybody agree with that? What is going to change if we, this is Koskals' algorithm on the original graph. We've sorted the edges. Here is Koskals' algorithm on the sorted edge plus the new graph edge, right? Koskals' algorithm will, by definition, do the same thing up until that new edge we added, right? What is the consequence of this? If the red edge would go between something that all these edges already formed a connected component, we would not take the red edge, and it will not change the minimum spanning tree, right? If, on the other hand, it was lighter than one of the other blue edges on that cycle that we were going to have to pick later, what's going to happen? We're going to take that red edge instead of that heavier blue edge. Because when we got around to inserting this, trying this edge, it would now create a cycle. So that's the argument as to why it is correct. Any questions about that? How many people sort of feel they're getting it? People are not getting it. All right? Good. Any questions? Okay. That's minimum spanning tree. There is sort of a brother graph problem to minimum spanning tree. And that is the problem of shortest paths. Okay? Finding shortest paths in a graph is a very, very important application problem. One that you probably believe is an important application problem more readily than you believe minimum spanning tree. Right? Why in a graph might you want to find the shortest path? Someone give me a graph problem where you have a shortest path problem. Yes. GPS system trying to send you, I guess, right, now you have it, your GPS system, you're sitting in your car. You say, take me to Manhattan. You hit return, and it's going to come back and tell you the fastest way to get there. Right? What? Okay, so your question is saying, yes, you want to take the shortest path while driving, where the shortest path is probably in terms of time, right? If we were worried about trying to save time, it would be to minimize the drive time, which is going to be the sum. The drive time is the sum of the weights of the drive time you spend on every leg of your trip, right? You might alternately want to minimize, okay, the distance you travel. Let's say you want to save gas. Is it possible that the shortest trip in terms of miles is not the fastest trip? What would be an example of that? Or a reason, or why would that be? Right, so one thing I've noticed is that, again, we occasionally have academics from other departments visit the university, and they have to give a talk in the morning. The ones that show up late always tell me the same thing. Oh, I was coming through New Jersey, and I followed MapQuest, and it said that the shortest way to get from New Jersey to Stony Brook is through Manhattan during rush hour. Okay? Traffic might be the shortest in terms of distance, right? But at any rate, I claim that there is clearly a class of problems that everybody here understands, where you have a network of things, of possible choices, and you want to get from here to here in the optimal way. That, I claim, is a shortest path problem in a graph for most reasonable such optimization problems. Any questions about that? What other things show up in shortest path problems? One problem that I was once asked by a former student of mine, went over to go to work for a video game company, okay, or a computer game company, and he was telling me, I have this job where I am animating. There's this game that's going on, and there are these characters who are sort of secondary characters whose job it is to walk around in the background. They look like they're doing something. Does this seem familiar to people in a video game? Sometimes you have the background characters are doing something, right? And if your background character is walking from here to there and back and forth, that doesn't look very realistic, right? What person is sitting there walking back and forth in eyesight? Very distracting. So he said, how can I come up with a reasonable thing for this character to do? So what did I tell him? I said, put him at one point, tell him to go someplace else and find the shortest path. Then he's going to be walking like he has a purpose to doing it. Does that make sense? I don't know if that makes sense in that example or not. But the claim is that natural people tend to follow shortest paths. So if you want to make somebody look like they're a person with some business, give them a place to go and get them to go there. Any questions about that? That should be reasonable. Yes, questions? Well, if we were going to, I mean, how did you get here to my class? Assuming you wanted to get to my class, may have been debatable, you probably followed the shortest path to here, right? If we were trying to show you, said, oh, I have to go get to Skeena's class in the video game, and I'm doing this, that looks pretty silly, right? That's basically all I'm trying to say. Any questions? Certain network problems become shortest path problems. Okay? Suppose you want to get an idea as to how good your network is from a communications network. Here's a question. Which is a better communications network? Okay? Let's say you have a bunch of computers connected by a network. Here you have a bunch of computers all connected by a network. This is one topology, this is another topology. Which one is the better topology? The star. Why is the star a better topology? Well, one of them you're saying is a security point of view, a robustness point of view. But the truth is, if you break any node, somebody's unhappy. Okay? So I'm not sure I believe that so much as why a star is a good thing. Why is it that a star is a good thing in a communications network? Because it minimizes the travel. Every pair of nodes are at most 2 hops apart. Does everybody see that? Here you want to send a message from here. Bop, 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 bop. Long communication delay, right? With the star, bop, bop. You're there. Any questions about that? So suppose you want to figure out what the worst time is. The maximum amount of time it will take to send a message from someplace to someplace else. I claim what you want to do to figure out which pair of nodes are the farthest apart, what we call the diameter of the network. You would want to find the shortest path from here to every other node, from here to every other node, from here to every other node. The longest hop is the maximum delay. Any questions here? Longest delays come up in circuits, by the way. I don't know if you think about computer circuit layout problems. Right? We had this idea of computer circuits. Digital electronic circuits can be modeled as a graph. Suppose you have a computer. Remember, computers are really electronic circuits. There's a clock that's going, right? You have how many megahertz or gigahertz your computer is? What is that referring to? That's referring to how many times the clock cycles per second, right? And each cycle says, bunk, do something, do something, do something. Why is it that your computer can only run 100 gigahertz? Why? Let's go back here for a second. Why is it that your computer is limited, let's say, to 1 gigahertz? Why don't they let you jack it up to 10 gigahertz? It doesn't work right. Why doesn't it work right? It's because you've got circuits that have certain propagation delays, right? On each cycle, your data has to flow around and finish doing its thing, right? And that time is basically governed by how many hops through this network, this circuit thing that is making your computer go. job it is to analyze the timing of digital circuits. They solve shortest path problems all the time. How many people see what I mean by this application? Does this make sense? Okay. How many people don't see what I mean? Any questions? Okay. So shortest paths are your friend, because computing a short path is something that algorithmically is an easy thing to know what to do. Okay, I will show it to you today or tomorrow, the right way to do it. Okay, today or next class, the right way to do it. What is important, though, is to see that there are lots of problems that reduce to really finding the shortest path. So when I am asked to solve certain problems, I'm usually not designing a graph algorithm from scratch. I am banging it into one of the few algorithms I have taught you and tried to figure out how to use it. Let me give you one other application of shortest path to sensitize you to where it might come in handy. Okay, we had a project. This is one of the war stories in the book where, again, you guys actually now all have cell phones. You guys all, how many of you type text in on your cell phone? Okay, a lot of people don't do that. I don't do that. But a lot of people seem to do that. Okay? And what is a problem with this? One problem is that on your cell phone, you have A, B, C, D, E, F. Does everybody see that there's 3 keys, letters on each key? So when you type in Skiena, you go pop, 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 whatever it is, right? How do you know that you're typing out Skiena versus, since every letter can have 3 possibilities, okay? It's possible that the real interpretation of it, if you just hit that key, there's ambiguity. Does everybody see that? 1 key press, 3 letters on the key, ambiguity. Regular typewriter keyboard, 1 key per letter, no ambiguity. Okay? But cell phones are smaller, so you have to have that. Any questions? So we were building a system. We were trying to figure out a way to figure out if somebody types something in, there's a stream of phone tokens. Could we figure out what they meant to type? Okay? And how might you do this? Okay? Well, one idea would be, if you have a thing for an end of word symbol, you could have a dictionary. And for every sequence of tokens that represents 1 word, you could go to a dictionary and find out what words have matched that phone token. It turns out that some symbols of phone numbers make there's a lot of words you can make from the same 3 letters. If you phone in cow, cow happens to be the same 3 letters as boy. It happens to be the same 3 letters as box. It happens to be the same 3 letters as any. Okay? So you might say, well, we'll figure out what words are hashed to the same set of phone keys. But of course, there might be collisions. If you want to figure out what the right sentence is, you've got to figure out which is the right words that make the most sense for a sentence. So here I have hive and give, of and me, ring, ping, sing. Okay? I claim that out of those, give me a ring is the logical interpretation. Any questions about that? Okay, see what problem I'm trying to solve? Given that I am given words that are possible in each column here, I want to find what is the right sentence that describes what those words, to make up from those words. Okay? Any questions about that? How might I do this? Let's think about it. How might you do this? How might you figure out? Yes, you. So you might use grammatical rules. Okay? How do you think of grammatical rules, though? Let's say that there's a noun and a verb. How would you implement this thing with grammatical rules? I agree, grammatical rules is probably a good thing, right? You probably know that certain pairs of words like to be next to each other. Give me is much better than hive of, or hive me, or hive of. Does everybody see that? Or give of. So maybe what we could do to factor in grammatical rules would be the following. Model this as a graph. What is interesting about graphs? Well, we can model it as a directed graph where there's a start of a sentence and an end of a sentence. In each case, we are passing from a word in the first position to a word in the second position. This can be modeled as an edge. And the cost of that edge can be how happy are these two words next to each other. Does everybody agree with that? Maybe we could go and analyze a dictionary or analyze all the text that's on the internet or something like this to figure out for every pair of words, how happy are they being next to each other? Okay? If we have a popular word here and a popular word here such that both occur in the news a lot, that should be given a low cost. If we have a rare word next to another rare word that doesn't appear in the news together a lot, that should get a low cost, right? What about two popular words? You know, tree, the. Tree is a popular word, the is a popular word. Maybe they don't go next to each other very much. The tree, not tree, the, right? I claim we can assign a weight reflective of how happy are they